speaker today, Professor Albert Cheng. Albert got his PhD from the University of Texas, Austin. He's now a faculty member in the CS department of the University of Houston. Albert is an expert and very prolific, I guess, in the area of real-time systems. He's published extensively in the leading journals and also conferences in the area. Now, in particular, his publication about incremental debugging of real-time systems was a feature article in last year's Iterative Transactions on Computers. So today, actually, he will talk to us about that topic, and as a bonus, he will also describe some of his recent work on security for embedded systems. So I'll give the time to Albert.
Thank you, David. Yeah. Okay, so the first part of the talk and major part of that is I'm going to talk about the debugging and verification of real-time and embedded systems specified in real-time logic, which is a first-order logic extended with the capability to annotate time, absolute time. So first, some preliminary introduction to the work, because I think many of you may not be familiar with real-time logic. Basically, this is a logic that was motivated by basically conventional logics like CTL and other linear time temporal logics cannot model time well, so they are capable of specifying related ordering of events, but not assigning time, absolute time, to these events and actions. So real-time logic was born in the late 80s. Basically, we can specify a system in a behavioral fashion, so we do not need the structural functional description, which allows you to actually build a system. So here we are able to specify the behavior of the system, and that's good enough for most purposes of verification. So an implementation is correct if the SP, the safety, the specification of the system implies the safety assertion. So SP implies SA is a theorem. So that's the objective of verification here. Now, there are three possible cases when you attempt to do this verification. First, SA is a theorem that can be derived from SP. So that's good. The system is safe. The second possibility is SA is not satisfiable with respect to SP. So here you have an engineer or a designer who doesn't know what he or she is doing. So the specification is completely wrong. But most likely, the third case occurs. So the system is safe if additional constraints are added. So you have the negation of the safety assertion, satisfiable under certain cases. So this is a situation where you most likely find this technique and the tool implementing this technique to be useful. So even an expert programmer or designer can make a few bugs the first try. So this tool is able to basically identify these problems for you. And here the focus is on the timing properties as opposed to the logical occurrence properties. Now, here in this talk, I'm going to introduce an incremental approach for debugging. So what happens if the verification tool tells you that there is a problem in certain areas? So this tool is able to tell you automatically what kind of constraints to add or to modify to make this into a correct specification. And this is the high-level look at this algorithm. So with a timing constraint that I have 15 minutes to look at basically two projects here, I'm not able to talk about the details, but I'll be happy to discuss some more after the talk. So here you have basically a loop, and we incrementally add new constraint until the system is safe. So SP implies the safety assertion. Okay, specification implying the safety assertion. So basically, okay, in step 3, okay, we are adding this new constraint, and later on we'll discuss a little bit how these constraints are created and how they're actually added to the system. I guess feel free to stop me if you have questions in real time, and I'll be happy to answer that question. So let's look at the details of the approach. Here the satisfiability of, if you go back here, so we are doing this incrementally starting with k equals 1, and k is incremented each time we add a new constraint. And basically we like to check whether this new constraint make the SP, the new SP, closer to the correct specification. Okay, that's what we mean by incremental here. If it's going farther away, obviously we do not like that constraint. So originally, we are doing this systematically, meaning that there's a method, but it requires users' intervention, so users' suggestion to see to tell the system whether this constraint is going the right way. But eventually, we would like to have the system behave autonomously, so that the system can be implemented in a robot, and it can check new plans, and the specification is written in this RTL, real-time logic language. So the satisfiability of the SP at the k+1 step, implying SA at the k+1 step, is expressed incrementally. Okay, from the previous, basically, it's not a theorem. It's what we are going to see if it becomes a theorem. Now we're going to use the counting SAT problem rather than the regular SAT, and the reason is because this allows us to know how far away the SP is from satisfying SA. And the modification of the SP and or SA is going to be useful in this debugging process. And bugs are fixed one at a time until the system is correct. That is why it's not good, to use this tool if your system is completely wrong. It would take a long time to be able to complete the debugging. But most of the people who develop real-time systems are basically experienced in the domain. So more likely you're making a few mistakes rather than a lot of mistakes. So motivations for this. Industrial systems, real systems are going to have large specification, not something you can feed into a standard conference paper. So it is impractical for a system designer to be able to go through this manually, even if you have a team and with regular software to find this missing constraint. So we need to have a tool to do that, and we call this tool ADRTL for systematic debugger for real-time logic. So let's look at real-time logic and look at some of the features and syntax of this language. I'm just curious if you have seen or know something about real-time logic. Maybe raise your hand. Okay, only one or two. So because of the time constraint, I may not be able to go over all the details, but at least I'm going to show you the key features. And the key feature is the occurrence function. Okay, it's we use this add character to indicate that. And basically, this is an assignment of absolute time, integer absolute time, to the instance of a specific event. So for example, this is the 15th time I press this button here, okay, the arrow button to go to the next slide. So I can say this occurs at time 4:39 and with 20 seconds. So I can do that in this language. Okay? So here you can see the occurrence time of the ith instance of event E is at time t. Okay, so the ith occurrence of event E occurs at time t. So I can write formulas like this embedded in just conventional first-order logic. I can specify here, for example, this is the next instance. Okay, I+1 is the next instance event.